Welcome to Visual Algebra Lecture 2.10, Examples of Semidirect Products. In the previous lecture, we began with a visual inflation method of constructing a Cayley graph of a direct product of two groups A and B by sticking in identical copies of a Cayley graph of A into nodes of B. We then learned about structure-preserving rewirings of a Cayley graph called automorphisms. This allowed us to construct the semidirect product of A and B by sticking in rewired copies of A into the nodes of B. In this lecture, we will see several explicit examples of this. We'll start with C5 and C4 because we can construct two different nonabelian groups of order 20 in this manner. We will also see how there are four semidirect products of C8 with C2, all of which we've recently seen. Then we'll construct the smallest nonabelian group of odd order via a semidirect product. We'll conclude with a surprising fact about the dihedral groups. This lecture has a lot of pictures, and I think that even experts on semidirect products will get new insight from it. Okay, let's get started. First of all, if you have not watched the previous lecture, please do so first. In it, I define things like rewirings, the inflation process, labeling maps, balloons. These are very non-standard terms. Now, I will give a recap, but this is meant as a refresher for those who have watched it, not as a replacement for those who have not. So consider groups A and B and a structure-preserving map from B to the automorphism group of A. This is the set of rewirings. We call this the labeling map because we're labeling each node in B with what rewiring we are going to stick in it. The semidirect product of A and B with respect to this map is constructed as follows. We inflate the nodes of the Cayley graph of B, and I think of B for balloon. Next, inside of each inflated node, we stick in a rewiring of the Cayley graph of A, and this map up here tells us how we do that rewiring. And then for each edge between nodes in B, we connect corresponding pairs of nodes from A. So here's an example of that. We start with a copy of C2. We inflate these nodes like balloons. We stick in rewired copies of the Cayley graph for A. And this identity and phi, these are the labels that are given by this map. And this says stick in the standard Cayley graph for A up here, and here stick in a reversed copy of that. And then we pop those balloons, and here is our semidirect product. Here's one more recap from the last video, because this will be our first example. There are four rewirings, i.e. automorphisms, of the Cayley graph of C5. So here's that graph. And remember, there are four generators of C5, either A squared, A cubed, or A4. So each rewiring can be thought of as sending this red arrow to one of the different generators. And I say that it's generated by the doubling map, because if we can think of phi, this one here, as what we get by taking each red arrow and doubling it. So instead of a path from arrow from 1 to A, we do a path from, we do red, red, and we go from 1 to A squared. So each red arrow here is replaced with a double red arrow here. And if we repeat that process, if we double one of these arrows, so replace red, red with just a red here, then that's the quadrupling map. And then if we do that again, we replace red, red with red here, we get the map that is the tripling map. Algebraically, what we're doing is we are squaring each generator. So A squared is A squared. Then we square A squared, we get A to the fourth. And then we square A to the fourth, we get A to the eighth, which is A cubed. The exponents are done mod 5. These four rewirings form the automorphism group, and here's a Cayley graph here. So these three are all generated by iterating this process. And so here's that Cayley graph, and here's what it looks like if I actually stick these rewirings inside of the nodes. And that's how we're going to build our semidirect product, which we talked about in the previous lecture, but now I'm going to do some examples. Let's begin by constructing a semidirect product of C5 and C4. So the first term is A, that's the thing that gets rewired, and the second term is B, that's the thing that gets blown up like balloons. So here is the automorphism group of C5. It's a coincidence that it's the same as C4. And then a labeling map is going to tell us how we are going to stick these rewirings into these nodes. So the simplest one is where we just stick this first rewiring phi into the node B. And by the rules of rewirings, which we did in the last lecture, that means that if we follow the blue arrow, we rewire. If we follow the blue arrow twice, b squared, we have to rewire twice. So we have to stick phi squared into here and then phi cubed into here. So what we're really doing is we're saying sticking phi squared, and phi cubed into here. That means that we're in each balloon b to the k, we're sticking in phi to the k. So that just sticks these rewirings into the nodes, the balloons, like this. And here's what we have. So here are those 4 rewirings. And remember, in the last step of the semidirect product, we connect up pairs of nodes. So there's a blue edge here. And so we put a blue edge from each one of these to its twin down here. So connecting these two from this A to that A and so forth, and we get something that looks like this. And you can see what we're doing for each of these. For this blue node, we put 5 blue nodes here and so forth. And this is our Cayley graph for the semidirect product with respect to this labeling map. Now, let's construct a different semidirect product. I'm going to use a different labeling map. Instead of sticking phi into this node, I'm going to stick phi squared into here. So now if I follow the blue arrow, I rewire twice. I do phi squared. So I'm going to stick, let me get a purple color. I'm going to stick phi squared in here. So if I follow the blue node twice, or the blue edge twice, then I stick phi squared in it. So phi to the 4th, which is phi to the 0. And then if I stick it in there, if I do it 3 times, I have to stick in phi squared cubed, which is phi to the 6th, or phi squared. So this is how we fill in the blown up nodes. Going down here, this is the identity rewiring. Here is phi squared. Here is phi to the 4th, or phi to the 0. And here is phi squared again. So we're alternating. Instead of 0, 1, 2, 3, now we're going 0, 2, 0, 2. And when we connect up the edges like this, we get what at least looks like a different group. So let's compare these side by side to see if they really are different groups. In the previous lecture, I talked about how there's 2 ways to canonically visualize what we're doing. One of them is by rewiring the edges of A, and the other one is by fixing the edges and relabeling the nodes. So most of the time, we'll prefer the rewiring the edge version, and I think this slide will show you why. So here's what that looks like. We fix the position of the nodes, but for each of these, we are rewiring the red edges. Instead, if we were to force that all of these edges have these 5 cycles, that if we fix the position of the edges, in other words, we say the first node is going to be B, then we have A squared B in the second column, and A to the 4th B in the third column, then AB, and then A cubed B, like this, then we will get a 5 cycle of red edges here, but it's going to tangle these blue edges. So if we shuffle, so what we're doing here is we're relabeling the nodes, whereas here we're fixing the node position and rewiring the edges. So I hope you agree that this is, probably a little bit preferred to this. And here's what we get for the second one. Notice how here's the original 5 cycle. If we rewire it twice, or rewire via phi squared, we get the reversal of everything. So in each row, we get an alternating direction of these 5 cycles. And I think this is a little bit prettier than if we were to fix the, if we were to force these cycles to go in reverse, that would mix things up a lot. And this is what we get when the cycles are all parallel, but the nodes are relabeled. So the blue edges are tangled. Now, I claim that these are actually different groups, but I'm not going to tell you right away how to do that. I want you to think about that. How would you prove that one of these has a property that the other one does not? And also, once we figure out that they're different, think about how you'd figure out which groups these are. But first, I want to construct another semidirect product of C5 and C4. And this time, I'm going to stick in this node, instead of phi or phi squared, I'm going to stick in phi cubed. And that's going to force this next node to be phi cubed squared, which is phi to the sixth, which is phi squared. And that's going to force this one to be phi cubed cubed, which is phi to the ninth, which is just phi to the first. Now, if we connect everything up, you look at this, it's basically the same thing that we got in the first example, except the blue arrows are in the opposite direction. And that's not going to actually change anything. That's just how this example differs from that one is instead of, if we replace every instance of B with B inverse, think of that as if this is like a rotation by 90 degrees, well, we're rotating it the other way by 90 degrees. We're saying we're switching what the positive direction is. Now, that's not a proof, but something that when we learn about this in chapter 4, we can formalize that so-called automorphisms like this, certain changes like this aren't going to actually change the isomorphism type of the group. Now, there's actually one more semidirect product we can do, and it's the direct product. Remember, the direct product is a special case of a semidirect product, and that's where in each of these balloons, we stick in the identity rewiring. So here's that labeling map mathematically. Here's what it looks like in terms of balloons. And here's what it looks like when we actually stick the unrewired copies in the nodes and we connect them up. This is the Cayley graph for C5 cross C4. It's worth pondering some questions because a lot of this I'm doing based on your intuition without proving things. The first question you might want to ask is, does this construction actually yield a group? Now, we've seen in chapter 1, when I showed you the formal definition of a group, I think that was lecture 1.6, we saw a graph like this that looks like a Cayley graph, and it looks like a semidirect product construction, doesn't it? This rewired copy in the middle, but it's not actually a group. And you remember why that was? So if this were a group, it would have order 10. And it's not abelian because red or RS is not SR. But if you look at this node, this element RS, red, blue, 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 that has order 10. So somehow this would have to be a cyclic group generated by RS, but it's not abelian because RS is not SR. So that's not possible. So how do we know that we're not constructing something like this with this process? That is one reason why we do need this formal mathematical definition. Another question we might have is, when do two labeling maps give isomorphic semidirect products? Hopefully, it seems reasonable that the first and the third one that I showed you earlier give the same Cayley graph, up to just reversing the arrows of B. But in general, it's just how often is this going to happen? What if there's 18 rewirings, and how do we know that we might not get 4 of them that are the same? And finally, is a semidirect product commutative? So if we can take the semidirect product of C5 with C4, can we do it with C4 and C5 and get the same answer? Well, the answer to that is no. Is unlike the direct product, we can't always get this to work if we stick rewired copies of B inside nodes of A. Next, I want to ask, which groups did we encounter when we constructed these semidirect products of C5 with C4? It turns out that there are only 3 non-abelian groups of order 20. They are the dihedral group D10, the dicyclic group Dic10, and this one that we haven't seen yet, but we'll see learn about more in an upcoming lecture, which is the one-dimensional affine group AGL1Z5. So this is the group of affine transformations over the field Z5. So that just means groups of functions so an affine function over Z5 is going to have the form f of x equals ax plus b, and it's invertible if a is non-zero. So we have 5 choices for b, any number will work, and 4 choices for a, 0 will not work. So these form a group. Sometimes this is called a Frobenius group, which is denoted either FR20. I think the group names in LMFDB database call this F5 for the Frobenius group corresponding to an affine transformation over Z5. And you might also see FROB. But anyways, with this knowledge that I'll say we can assume, if I give you a Cayley graph, how would you figure out which group it is? So probably the easiest way is to understand the order of the elements. So the dihedral group is going to have 11 elements of order 2. It's got 10 reflections and 180 rotation, right? And it's going to have 0 elements of order 4 in particular, because there's no reflection of order 4 and there's no fourfold rotation in D10. Now the dicyclic group has 1 element of order 2. Remember, that's -1 or r to the n over 2. And then remember that half of the elements of this are going to have order 4. All of the elements that have that s in them, or the j. Remember the Cayley graph looks something like this, and that all those inner circle elements are going to have order 2. So there will be 10 elements of order 4. And also, both of these things have 4 elements of order 10, namely r cubed, r to the 7th, and r to the 9th. 1, 3, 7, and 9 are the things that are relatively prime to 10. So it turns out that this affine group does not have any elements of order 10. They all have order 1, 2, 4, or 5. So if we take a Cayley graph and we start looking at the order of elements, we can quickly figure out which of these 3 groups it is. And let's do that. Here are those Cayley graphs again, and I hope you don't mind if I work with these 2 rather than those 2. So I'm going to write down the order of the elements by the nodes. This has order 1, and then these all have order 5. And then b has order 4. B squared has order 2. B cubed has order 4. And then let's use some reasoning to figure out what the order of the elements in this row is. So I claim that these all have the same order, and here's why. So I haven't proven it. We will do this. It'll be very simple in chapter 3. We just don't have the tools yet. But the order of any element has to divide the size of the group. So the order of G is 1, 2, 4, 5, 10, or 20. Now, this is a non-abelian group, so it's not cyclic, so 20 is not possible, and it's only going to be 1 if it's the identity. So let's think about AB. So we do red, blue. We go over, down. Red, blue. Red, blue. Red, blue. And every time we do AB, we advance a single row. We keep doing that. So the order is how many steps it takes till we get back to the identity element 1. And if we're increasing 1 row at a time, and there's 4 rows, then whatever that is has to be a multiple of 4, right? And the only thing on this list that's a multiple of 4 is 4 itself. So that means that AB has to have order 4. And the same argument works for all of these things. So red, red, blue. Red, red, blue. We're going down 1 row every time we apply that. So all of these things have to have order 4. And let me go down here for a moment. It's the same argument, 1, 5, 5, 5, 5. The fact this is a different group, we're still, for all of these elements, we're going down one row. So these things all have to have order 4. And by the same reasoning, everything down here has to have order 4, because there we are, you get down here, we do some number of reds up here, and then we go down, we do backwards blue. So we're traversing the rows in the backwards order, reverse order. So it will take 4 steps to get back to our home row. And so the order has to be a multiple of 4, and that's the only possibility. So all of these things have to have order 4 in both of these groups. So what about this middle row? So here, for this middle row, we are increasing the rows by 2. So every even number of steps, we're going to end back in our home row. So that means that the order of a b squared has to be even. It can't be 5. So it's either 2, 4, or 10. Let's see what this is. So red, blue, blue, red, blue, blue. That has order 2. Let's do the next one. Red, red, blue, blue, red, red, blue, blue. That also has order 2. See the pattern? This one here, red, 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 blue, blue, red, 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 blue, blue, blue. For all of these elements, their square is going to be b squared. So this is order 2. This is order 2. Oh, sorry, I said that wrong. Red, blue, blue. The path goes through b squared. Yeah, the square is not going to be b squared. Red, blue, blue, red, blue, blue. Red, red, blue, blue, red, red, blue, blue. But these are all in order 2. So right here, we have a group that does not have an element of order 10, and it's a non-abelian group of order 20. So it has to be that affine general linear group over Z5. Let's go down here. What about AB squared? Let's just check it out. Red, blue, blue. Red, blue, blue. That's 2. Red, blue, blue is 3. Red, blue, blue is 4. Red, blue, blue is 5. So if it takes 5 steps to get here, then it's got to have order 10 because it's more than 5. And yeah, you can check red, blue, blue, red, blue, blue, red, blue, blue, red, blue, blue, red, blue, blue. So this has order 10. And now I'll make several comments. First of all, if an element has, if let's call this thing R, if R has order 10, then we know that, so if R has order 10, then R cubed, R to the 7th, and R to the 9th have order 10 as well. Also have order 10. Other thing I want to mention is that once we determine that the order of, what was it, a b squared to the 5th equal b squared, or not the order, if we take a b squared and we did it 5 times, we got here, we could take this equation and square both sides. We get a b squared to the 5th squared, which is ab squared to the 10th, equals b to the 4th, which is the identity. So we didn't actually have to continue. We could have deduced right away, but we knew that because we knew the order was bigger than 5. So you can check that all these things have order 10, or you can just, you know that has to be true because by this argument, this is a cyclic subgroup of order 10, and there's 4 generators in that. So this is either the dihedral group or the dicyclic group. You remember which one it is? Well, there's these elements of order 4 that will eliminate the dihedral group, which has no elements of order 4. So this thing has to be the dicyclic group, Dic 10, of order 20. So hopefully this shows you a lot of things. First of all, gets you to understand these semidirect products, how they are like twisted versions of the Cayley graph in here, but also just how useful it is to have these Cayley graphs. Like, I could give you a presentation for this, and let's do that. Let's write a presentation. This first one is generated by A and B. A to the fifth is equal to B to the fourth is 1, and then what? Well, we somehow have it suffices to describe how this row gets twisted. So if this were untwisted, it would be red, blue equals blue, red. But what do we have now? We have red, blue equals blue, red, red, red. So we have A, B equals B, A cubed. And that's enough to describe what this rewiring is. And that relation is going to hold everywhere. Down here, we have the group generated by A and B, same beginning. A to the fifth equals B to the fourth equals 1. But now AB equals B, A to the what? So red, blue equals blue. You could say A inverse or A to the fourth. So blue, red, 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 red. So changing this 3, well, if this A is a 1, we get the direct product. If it's a 3, we get this one. And if it's a 4, we get this. Think about what happens if it's a 2. I'll let you think about that. So somewhere we had this third direct product that we didn't actually, that's the same as one of these. And yeah, it was the same as this one. And hopefully that should be pleasing, because you change this to a 2, it's not going to change the isomorphism type, but it will change up the Cayley graph. Our next example are some groups that we saw a few lectures ago, and it's not required to watch these lectures. I encourage you to watch my lectures on the semi-dihedral and semi-abelian groups. So in those, I took these two familiar groups, and I said, what if we erase these inner red arrows and ask, how can we rewire them to get a Cayley graph of a group? What we were really doing, I didn't say it, was a semi-direct product. And here were two different ways to do that. And from looking at this, it seems like these two have the most in common, and these two have the most in common. And that's just, if you were to ask someone in the street, that's probably what they would say. Let's construct these as semi-direct products now. There are 4 rewirings of the Cayley graph of C8, because there's 4 generators, 4 things relatively prime to 8, 1, 3, 5, and 7. And here are those rewirings. Notice that, unlike the previous example, all 3 non-trivial rewirings have order 2. So this is like the tripling map. You replace each red arrow with red, red, red. If you do that again, you replace this with red, 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 you get back to where you started. Algebraically, r cubed is r to the 9th, which is r to the 1st, mod 8. Over here, this is the quintupling map. If you replace each red arrow with 1, 2, 3, 4, 5 red arrows, you get this. And now if you do that again, 1, 2, 3, 4, 5, you get back to the node that we started with. And this rewiring is just the reversal. You can see that has order 2. You do it again, it reverses it. Again, algebraically, because 3 squared, 5 squared, and 7 squared are 1 mod 8, these have order 2. I claim there are 4 labeling maps from C2 to the automorphism group of C8, which is just V4. And remember, a labeling map just says, tell me which of these rewired diagrams I put in each of the inflated nodes of B. So we have to put the identity rewiring in the identity balloon. But for the other one, we have 3 choices. We can stick either of these, well, 4 choices. We can stick the identity one in as well. So here are the 4 labeling maps. And again, here's a Cayley graph for C8. It doesn't matter which 2 things you put here. You take any 2 things of order 2, and the third one's going to go here. And here are those 4 semi-direct products. Now, this one, you'll notice, is an example where I prefer the node relabeling rather than the edge rewiring. I think it's a little more insightful if I have these 2 parallel red arrows and we see how the blue arrows are tangled. So this in the upper left, hopefully you see, is C8 cross C2. This one in the upper right, I claim is D8. One hint is I use delta for dihedral. One way to see that is this bottom row of elements. I claim they all have order 2. Let's check. So SR, so blue, red has order 2. Blue, red, red. Blue, red, red has order 2. Blue, red, red, red. Blue, red, red, red. I think you see the pattern. All of these elements here are going to have order 2. So that's the dihedral group. Now these two things here, another way you could do that, let me just mention it, is we could check that relation. Here we have SRS. So let's write that down. SRS equals R. Here we have, this is a better way, SRS equals R to the 7th. So this is SRS equals R to the 7th. This is SRS equals R. SRS equals R to the 5th. So that is the semi-abelian group. And this is SRS. It better be R cubed. Let's check that. SRS, yes, is R cubed. This is the semi-dihedral group. And now I claim that these two actually have the most in common rather than these two. And let's think about why that is. So R4 commutes with everything in this group, so as does the identity. So in all 4 of these groups, these two blue edges have to be there. So notice how these two vertical blue edges are unchanged. It's the other 6 edges that determine which group we're in. And let's compare these two. So of the 6 possible ones that could differ, these things actually have 2 of them in common. There's this one from R squared to SR squared is in both of these. I'm gonna highlight this. Let me pick a different color. So that is the same as that. And similarly, this one is the same as that. So in the 6 possible edges, they differ in 2 of them. Notice that these two don't differ in any of those 6, and these two don't differ in any of those 6 either. So over here, let me pick a different color. I claim that I'll pick the same color. So it's a little harder to draw it, but this edge and this edge both appear in these two. So of these 6 edges that are like wild cards, this pair has 2 that are the same, dihedral and semidihedral, and as does this pair. And if you recall that lecture on the dihedral, semidihedral, and semi-abelian groups, one way to think, I had a picture that showed how the Cayley graphs differ, the inner edge differed by 180 degrees. And then I gave you matrix representations, and they all differ, and these two differed by a negative sign, as did these two in the 2-2 entry. So that's perhaps surprising from, when I first showed you the circular Cayley graphs, these two looked to be the most similar. But it also, if you remember, one of my students came up with the name semi-abelian. That's why I really, really like this name, because semi-abelian is to abelian, this abelian group, the way that semidihedral is to dihedral. And you also may remember that these two groups had the same cycle graph. These two did not, but as we'll see soon, these two have very similar looking subgroup lattices. And these two cycle graphs were not all that different either. A few lectures ago, I said that if n was a power of 2, then there were 4 non-abelian groups of order 2 to the n, or 2 to the n plus 1, equivalently, that had an element of order 2 to the n, this big red cycle that took up half the nodes. And those were the dihedral, semidihedral, semi-abelian, and then we actually had the generalized quaternion group. Well, that was not a semidirect product, but so if we kick that one out and we replace this abelian group in here, now we have a related theorem that says there are 4 distinct semidirect products of C to the n with C2. when n is a power of 2. And these four, they are defined by their rewiring maps. And this determined that last relation. This is SRS equals R, SRS equals R to the 2m minus 1 minus 1, SRS equals R to the 2m minus 1 plus 1, and SRS equals R inverse. The reason why this holds is because whatever rewiring we pick, it must have order 1 or 2. So the identity rewiring has order 1, but the others, if you do them twice, you get back to where you started because of the property of rewirings that phi of b squared is phi of 1, which is the identity. In other words, if you have the identity node and you have b, and you stick phi in here, then you have to stick phi squared in there, which has to be the identity. So that means that phi has to have order 2. And it turns out that there are only 3 elements of order 2 in the multiplicative group of integers mod 2 to the m. Remember this? This is the group that is, again, watch the previous lecture. This is isomorphic to the automorphism group of c2 to the m. And this follows from a result in number theory. It's not the easiest result, but it's something that you could do in an undergraduate number theory class. And that is for any n at least 3, the quadratic equation x squared is equivalent to 1 mod 2 to the n has exactly 4 distinct solutions, plus or minus 1, and 2 to the n minus 1, plus or minus 1. So if we think about that as a circle, so here is, so if this is 0, here is 1, here is negative 1, here is 2 to the n minus 1, and then here, so our solutions are going to be here, 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 and here. And if you remember that picture from the previous lecture, we had this, if we had a big red cycle here, and then we have all these, we have this partial Cayley graph like this, and the question was, how can we rewire these inner red nodes? So, or these inner red edges. And so from here, there were 4 possibilities. We can rewire it to 1, negative 1, and then 2 to the n minus 1, plus or minus 1. And that's due to this number theoretic fact. But once we have that, we get this theorem for free. The last example I do is the smallest nonabelian group of odd order. It is a semidirect product of C7 with C3. And we saw the rewirings of C7 in the previous lecture. Again, I really want you to watch it. And here they are. Here they are in a Cayley graph. We can stick them around the circle like this. And now we have to have, let's think about what we want. This is A, this C7, that's the thing that's going to be rewired. This is B, that's the thing that gets blown up like balloons. So we take B, C3, and we blow up the nodes like balloons, and we have to stick 3 of these things in here. Now, if this is so let's say that this is the identity map, and this is B, and this is B squared. Well, we have to stick the identity rewiring in here, and now we have to stick an element of order 3 in here. And in this, the automorphism group here of C7, notice that this is isomorphic to C6. So there's 2 elements of order 3, that's phi squared and phi to the 4th. So if we stick one of them in here, we stick phi squared in here. So the blue arrow means purple, purple. Phi squared, that means 2 blue arrows, means phi to the 4th goes here. So we stick phi squared here, phi to the 4th here, and we're done. And we had one other choice. We could have stuck phi to the 4th here, which would have put phi squared here, but I claim that we'll get an isomorphic group. So if we do this, here's what it looks like. I mean, it's a little bit, we could arrange these like we did before with these parallel blue lines, remember, like this, but that's just going to be messy. It's actually easier to arrange them with these rings, and I like to think of this as like a tunnel where these nodes are the furthest away and these are the closest. So it's like we're going into a tunnel here. But yeah, here is that first. So this node here is like this ring of nodes here. This inner ring is this rewiring. So it's like this outer ring is phi, the 0. This inner ring is phi squared, and this most inner ring is phi to the 4th. And I always have my students do this for C7, or sorry, for C9 and C3. And they get something a lot like this because the automorphism group of C9 is also equal isomorphic to C6. But it turns out that for that one, you can do the same labeling map, but phi squared ends up being a lot more tangled. It looks kind of like this. And so it's actually easier to draw this picture if you stick phi to the 4th in here and phi squared in here, because phi squared is the one that's tangled like this, and phi to the 4th is the one that is easier to, has more of an inside. Now, I almost wish I had included this in the lecture, but I'll let you pause this and check this out. If you go to the Wikipedia page on semidirect product and you look at the formal definition, it is pretty complicated. And even if you have a strong mathematical background and you're seeing it for the first time, it's tough to wrap your head around what it actually means. I think I will include it in the lecture we're in chapter 4 when I talk about semidirect products formally. But I hope that you will agree that this is really the intuition behind semidirect products. And the idea of these labeling maps and how you have to stick, if you stick phi squared in here, you have to stick phi to the 4th in here. You are understanding the concepts of homomorphism and structure preserving map before we get there. And again, the reason why I did this early is because there's a lot of groups that we've seen that have this structure, and there's new groups we can make that have this structure that I really don't want to wait until chapter 4 to show you. We'll use them a lot as examples in chapters 3 and 4 before we get to this. Okay, one last comment. We know that we can construct the dihedral group D6 as a semidirect product of C6 and C2. We actually don't need the subscript because there's only one non-trivial one. But it also secretly decomposes as a direct product. You may remember in the previous lecture, I put up a picture of 3 groups and I said 2 of these decompose secretly as direct products, and it's not the 2 that you think. Well, one of them is the dihedral group. To see this, let's draw a Cayley graph with a non-standard generating set. So I'll say D6 is generated by R squared, R cubed, and F. And if I do that, you can see that there's a direct product structure here. Maybe not clear why I did this, right? So I have R squared and F generating this subgroup, which is D3. And then I have another copy of that, and you can see that this direct product structure. And here are the actual nodes as ordered pairs of D3 and Z2. So this should be quite mysterious now. And think about how does it generalize to larger dihedral groups. I claim that if n is even, this is basically going to work. But also, why does it work? This is something that we will completely understand in chapter 4 when we study subgroups and automorphisms. There's a reason why this thing works, and it has to do with the fact that this element here, R cubed, commutes with everything. That's not a sufficient condition, but we will understand in terms of subgroups how to tell when a group decomposes into a semidirect product, and we'll be able to see that visually on a subgroup lattice within a matter of seconds. Okay, that's all for this lecture. In the next lecture, we'll talk about groups of matrices. So we will revisit those affine groups, one of which we saw in this lecture. We'll also talk about other groups of matrices like general linear groups and special linear groups. And we'll have some surprises, something called a braid group. And I'll talk about what does it mean if a group cannot be represented with matrices. Can you think of one of those? And then we'll talk about the Hamiltonians, matrix groups over finite fields, and we're almost at the end of chapter 2. After that, we'll have one lecture on other finite groups and what it would mean to classify all finite groups, which is an impossible task. But I'll show you some surprises. That will be a lot of fun. So stay with us.